Hello and welcome to the webcast titled Solving Military Sensor Fusion Challenges with AMD's Versal Adaptive System on Chips, or SoCs. My name is John McHale, Editorial Director with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. We've got a great lineup of speakers here today, starting with Ryan Jansen, Vice President, Advanced Technology for New Wave Design, Brett Bergstaller, Product Manager, New Wave Design, and Manuel Director, Versal Product Marketing for AMD Adaptive and Embedded Computing Group. This event is sponsored by New Wave Design and hosted by Military Embedded Systems Online and Open Systems Media Online. Now, before we get started, I've got some housekeeping items I want to go over with you. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will consume about 40 to 45 minutes, leaving the remaining time for the question and answer session. Let me show you around the viewing console here, give you a little tour. You'll find on the right-hand side an area where we can enter questions in real time. We encourage you to ask those questions throughout the session while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I'll offer it up to all of our speakers. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the webcast. And please note, as much as we'd like to, it may not get to all your questions today. In that case, someone will get back to you after the event with more information. Now, across the way on your screen, on the left-hand side, there's a resources section. That's where you can find today's slides and speaker information. Two additional features we're excited about. Your console is now customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. Expand them to get a closer look, or close them to have the presentation window automatically resize around them. For maximum screen size, you close them all or utilize the full screen control in the upper right-hand portion of the presentation window. Bring them back, simply click on the buttons in the bottom middle dock. In an effort to make all these webcasts more accessible, we have added closed captioning capabilities in nearly a dozen languages. To enable this functionality, just click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This webcast will be archived online at the same URL you used to join the live session and be available within 48 hours. Once up, it'll be available for at least 1 year. And now I'm going to turn over to Ryan to get us started. Ryan, take it away.
Thanks, John. So if you look at all the sensor processing and sensor fusion applications in the mil-aero defense market, you will notice that there's a large number of FPGAs across these platforms, and a huge chunk of them in our AMD UltraScale Plus, and other traditional FPGA families. As you know, sensor bandwidth increases and sensor fusion becomes more prevalent, and the ability to process across multiple sensing domains, it becomes commonplace. That puts even more strain on the hardware that's doing that sensor processing. And so you really want to take advantage of the latest silicon that is out there and available to you. The latest family of AMD FPGAs, which are now known as adaptive system on chips, really are well suited for these environments and these sensor processing applications. And they've really added a great number of new elements to these chips that you didn't find in some of the traditional FPGAs. So there is a bit of a learning curve, and they've diverged a little bit from the traditional FPGA architecture that you might be familiar with. But we think that added capability is really great, especially for some of these sensor processing applications and reducing and optimizing the swap for these applications as well. So today we really wanted to take a look at this new Versal series from AMD and share, some of the differences from some of the previous families you might be familiar with, and also what some of those benefits are, so that if you have an upgrade from a legacy platform, or you're doing a design on a next generation platform, and you want to take advantage of these parts, hopefully we can provide you some tips and tricks and some things to look out for, so you can mitigate risk as you're making that transition. So to start out today, we have Manuel. He's the director for Versal Product Marketing from AMD, and he's going to start off the session by just kind of giving an overview of the Versal family from AMD.
All right, thanks, Ryan. All right, so let's talk about AMD and Versal. So of course, I'll start out with the overall portfolio. At AMD, we have quite a large portfolio, as you can imagine, not only FPGAs and adaptive SoCs, but also, of course, evaluation kits, SOMs as well. And of course, a large, of course, major component of the portfolio is embedded CPUs, including Ryzen and EPYC CPUs for both client side and server side, as well as GPUs. Now, with that, let's focus in a little bit more on the adaptive SoC and the FPGA portfolio. So when we were designing the architecture of Versal and keeping in mind the timelines of semiconductors, this would have been literally about 10 years ago when we first started thinking through, okay, what's the architecture for the next generation of adaptive SoC and FPGA look like? And what we realized was, look, if you look on the left-hand side of the chart here, a lot of the laws that in the semiconductor industry we relied upon to keep semiconductors increasing in performance and managing power consumption were starting to slow down. So things like Dennard scaling, which is exactly a rule around performance and power consumption and trading those off. Things like Amdahl's law, which you'd see basically multi-core processing architectures start to diminish in terms of the efficiency. And of course, Moore's law, which most people are familiar with. So when we took all that into account, we started to see that if all we did was take the UltraScale Plus architecture at 60 nanometer and move that over to a newer node, actually what would happen in all likelihood is if we did nothing else but just port that over, is we would see performance increase, certainly, but we'd also see power increase as well. And of course, no one wants that, especially in this community where size, weight, and power swap are so critical. So realizing that, we took the approach we did, which was to create a lot of hard IP within Versal. So you can think of that hard IP as essentially ASIC-like blocks for things like Ethernet and PCIe, things that are going to be very commonly used for most applications. And by doing so, manage the power consumption while keeping the programmable logic so that you still have the hardware flexibility that you need for missions going forward, and especially multi-mission profiles and payloads. And then, of course, we also added the processor system, which we carried forward from Zynq UltraScale Plus, but carried forward to a newer architecture within ARM. And so that was kind of what was going on, the confluence of what came together to be the Versal architecture. Now, at the same time, we also saw the need for a new compute paradigm. And what we saw there was, if you look at all the various semiconductor processor architectures, there's CPUs, there's GPUs, there's FPGAs, and quite frankly, they're all good for what they were intended to do, but they can't do everything optimally, right? Because in an application with the type of complexity that you have with modern aerospace and defense systems, you have latency critical workloads that you have to manage. You have all kinds of different data types coming in from different sensors. You got to fuse that sensor data. You got to do algorithms. Sometimes you got to incorporate AI on that. You may have domain specific parallelism around video. So all these things need to be done in real time at low latency. And so what we discovered was you really need a heterogeneous compute solution. You need all three of those architectures. You need the programmable logic hardware flexibility, you need the CPU capability, and you need the GPU capability. And it's the combination of those in the right mix that is really the key to being able to achieve what modern aerospace and defense systems require. So that's what we did with Versal. And if you look at the portfolio, you can see, of course, it's a very large portfolio. Certainly, if you go back to 7 Series and UltraScale and UltraScale Plus, then you add Versal on top of it. And what I would say is, when you look at the portfolio and you look at technology today, Versal is really fitting in kind of the mid to high end, as you can kind of see in the diagram here. And what that means is, for the nodes and advanced nodes that we're using Versal, honestly, they're not easy and they're not cheap. And so we are targeting the mid to high end of the portfolio there. Now, UltraScale Plus is a 60 nanometer portfolio, and 60 nanometer is a fantastic, be very long-lived node. And so we're basically filling in the portfolio at the low to mid end with 60 nanometer plus. And you would have seen that with announcements like Spartan UltraScale Plus. Now, the nice thing with Versal, when you look at the portfolio, is you can see much of it is already in production. So you're utilizing devices and software and IP that are hardened, that are proven, been proven out in the field multiple times over in many, many industries. And of course, we continue to add to the portfolio. So we've announced things like AI Edge Series Gen 2, Versal Prime Series Gen 2, Versal Premium Series Gen 2, and Versal RF Series as well. And so when you look at the portfolio that we have today, it's extremely comprehensive. And despite the plethora of different applications you have within aerospace and defense, you will see that there is devices within a Versal series that could fit and cover that entire range virtually. Excuse me. So if you look at the top with Versal Prime series, that's basically the mid end of the devices. There is an option for high-end scalar compute, and that comes with Versal Prime series Gen 2. And so that capability, very powerful, very broadly used in a number of aerospace and defense applications. Now, when you're looking at the high end, and that could include things like high-end radar, electronic warfare systems, that's where you have things like Premium series, where they have a ton of additional connectivity and hard IP, but also a lot of DSP capability and a significant amount of programmable logic. Now, there is also HBM series, which adds high bandwidth memory to the Premium series, and it's it's an amazing capability bringing those two together, and it really adds a lot in terms of having that high bandwidth, very low latency memory because it's tightly coupled with the Premium programmable logic, and so it's a great fit also for some radar designs, things like DIRFMs, that type of thing. Then you go to AI Edge series, where we're really targeting inference at the edge there, but also traditional embedded systems where you're very size, weight, and power constrained. And so it's really end-to-end acceleration for embedded systems, particularly that at the edge, as you can imagine. And then AI Core series is really higher end compute. So there we've also got AI engines, which are also available in AI Edge. And that adds a lot of capability in terms of DSP capability as well as AI capability, because those AI engines fundamentally are vector processors. So they're linear math or matrix, linear algebra and matrix math, and they're things that are optimized for both signal processing and ML algorithms. And then you look at something like RF series, which has created a lot of buzz in the industry. And the RF series, of course, brings in analog capability in a monolithic design with the rest of the heterogeneous compute. So the programmable logic, the AI engines, the processing system. And so that capability really unparalleled. And when you look at this whole portfolio, it really does put together an amazing system level capability for modern aerospace and defense systems. Now with that, I will pass it over to Brett.
Thank you, Manuel. To give a brief, background on NewWave, NewWave is a hardware vendor as well as an IP vendor. So we have, a lot of experience putting down ultrascale plus FPGAs as well as Versal FPGAs. We also have a lot of experience doing designs for Versal FPGAs as well as ultrascale plus FPGAs. So, we wanted to go through some migration considerations that NewWave has noticed as we've upgraded or implemented Versal designs. So the considerations we're going to be going over, myself and Ryan, I'll be going over the SIPs and NOC, the programmable logic, the PL architecture. And I'll hand it back off to Ryan, and he's going to go over some transceiver updates with Versal, tool chains that are used with Versal, and board design considerations, and then a little bit more information on AI cores. So jumping into it with the SIPs and NOC and starting with the SIPs is the control, interface, and processing system. This is a required element within Versal configuration for reasons such as the PMC is part of the SIPs, and the PMC is controlling how your chip is booting, for example. So this, again, the SIPs was not an element that was present in ultrascale plus, and it is an element that is required in Versal. And the SIPs, it had things similar to it in ultrascale plus, like Sysmon, Startup, ICAP. Those sort of primitives are now organized into the SIPs. And you have, again, in the diagram, it's the red area. The SIPs contains the CPM, which is a PCIe piece of hard silicon, the processor system, the PS, which includes the APU and the RPU. And then, as I mentioned, it also contains the PMC. Moving into the NoC. The NoC is another new element. The NoC addresses, it stands for network on a chip. It addresses the need to route signals on the chip. The Versal devices can be rather large. They still have the concept of super logic regions, SLRs, in suitably large devices. So some devices have 2 SLRs, some devices have 3 SLRs. The NoC really helps you get, PL-based RTL designs, get your, signals from, one super logic region to another super logic region. They also provide another big benefit, and it provides hard silicon to hard silicon routing directly without using the PL at all. For example, you can do CPM, so PCIe transactions, directly into DDR. You can do PS-based, things from the APU, so your processors can access the DDR directly without using the PL. Examples like that, where it's hard silicon resources to hard silicon resources without using the PL at all. The NoC, one last comment, the NoC does also include DDR hard IP, which replaces the soft IP that UltraScale Plus used for the MIG. Moving into the programmable logic, where the SIPs and the NoC, those are relatively new elements that a UltraScale Plus user wouldn't necessarily be familiar with. The programmable logic, once you get into the programmable logic, this is going to have a very similar feeling, look and feel and use as UltraScale Plus. It's not exactly the same. In general, the primitives, so a DSP primitive or a CLB primitive, they're generally supersets of what was available in UltraScale Plus. But generally, the tools are going to be able to correctly infer UltraScale Plus RTL to the UltraScale Plus primitives, UltraScale primitives, as well as on the Versal primitives. As I said, they're supersets, so there is a set of RTL that's going to actually infer better on Versal. So to kind of, on these 3 slides, SIPs, NoC, and programmable logic, a way to mitigate risk on these topics, AMD does provide example designs that come with their example boards, basically. So that's a really good spot to start. If you're putting down, a VP1702 design, look at a VP1702 dev kit, and they're going to provide things like bootloaders and Linux, PETA Linux BSPs to get the PS up and running, as well as some, PL examples. So you have a really good spot to start with to, essentially get up and running and modify the example design to suit your application. And then further, usually a hardware vendor, so if, for example, New Wave is going to provide example designs that target their hardware specifically. And, other hardware vendors would do the same. So to mitigate your risk with the SIPs and NoC, you would really look at the, existing example designs that are out there. And regarding programmable logic, there shouldn't be much risk to mitigate there because tools should infer RTL designs correctly. With that, I'll hand it back off to Ryan.
Thanks, Brett. So the next thing I want to talk about are the transceivers. So, in these sensor processing applications where you have an extreme amount of sensor data to deal with, the transceivers are extremely important. You have, with these Versal devices, you have some very high-end transceivers, and you have a lot of them depending on the devices that you select. So those familiar, with the UltraScale Plus series, the transceivers, using them, the setup should feel very similar. You still have the transceiver GUI to set things up. You can still tweak a lot of the settings for certain protocols, or make use of, the extensive hard IP blocks that are there. Within the Versal series, you're going to have the GTYs, GTYPs, and GTMs, 3 different types of transceivers, which can range in data rates down from 1.25 gigabits per second all the way up to 112 gigabit per second PAM4. This allows you to do things, like the 100 gig Ethernet and beyond, and all the way down to 10 gigabit per second Ethernet, all in hard IP. And that feature is really something that we've appreciated in that Versal family, is just the extensive amount of hard IP that is available. So not only can you do all those different rates of Ethernet, you have a CPM block for PCIe that fully contains the PCIe IP core as well. So without even having anything in the programmable logic, you can have a PCIe endpoint up on that Versal device. In addition to that, there's interlocking cores, high-speed crypto cores on some of these pieces. So the amount of things that you can get done without even taking up any of the programmable logic really saves you a lot of time and space for your own user applications. And as Manuel mentioned earlier, because those things are in hardened IP, you're going to get better power performance for doing those things as well. Oftentimes some of the hardest challenges we have are not, implementing some of the latest high-end, 100 gig Ethernet links and beyond. It's actually some of the lower speed things. If you're upgrading a platform and you have a legacy sensor that, might be doing 1 gig fiber channel or some proprietary AP10B protocol, that drops in below the rate that is actually supported by these transceivers. There is, AMD does provide a really nice IP block for that, a soft IP block called the NIDRU, which is a non-integer data recovery unit, which does allow you to do some oversampling, and you have a lot of flexibility to dial in the rate that a specific protocol needs to run at. So you can still handle some of those legacy sensor interfaces in these designs too, but you're really gonna notice the power and capability when you move into some of the more modern high-speed interconnects. In addition to that, there's some transceiver PLL updates as well with the new device. We find these things really helpful because you now have more flexibility and you can generate a wider range of user clocks based off of a single reference clock. So if you're designing a board where you need to be flexible and handle a lot of different high-speed serial interfaces and protocols running at different rates, your clocking architecture on the board can be simplified, making use of those PLLs. And then finally, I just want to touch on a few notes that are different and are a little bit of a departure from what you may be used to on previous generation FPGAs to keep in mind as you are making a transition to Versal. And the first thing on here is that that CPM, that PCIe hard block that we talked about. Those transceivers that go to that block are dedicated for PCIe only. So you lose a little bit of flexibility that you may have had in previous designs where you could use those for PCIe in one design and Ethernet in another design. Now those are going to be PCIe only. And, in like a 3U VPX card, routing some of the high-speed serial lanes to the expansion plane, for example, you may lose some flexibility there, or you may have to implement other things in your board design to accommodate for that. The next thing is they're high-end transceivers, the GTMs that are doing, going all the way up to 112 gigabit per second PAM4. The first generation of those and the first gen Versal parts do not support PCIe. So there you have to be careful when you're deciding which transceivers go where and what protocols you want to run on them. Be aware that those do not support PCIe because of there's no electrical idle. So even if you wanted to implement a soft PCIe IP core, that would pose problems for you. And then finally, with all of this hardened IP, it's great. You can see on the diagram to the right here on the outside in different shades of green, you have all the different types of transceivers. And then down the middle, you have all the hard IP blocks. There's rules for which transceiver quads are compatible with which hard IP blocks. and which locations can go to which hard IP blocks as well. So when you're doing a design, especially a board design at the beginning, the transceiver quad selection can be extremely important depending on what your design goals are, and the way you choose some of those and where they go. You can end up with a board that's really flexible or maybe not as flexible. So we recommend putting a lot of effort into this part of the design, and also be sure to run through, at least some example designs of what you're trying to do in the tool itself, just to verify that you can run the hard IP protocols with the transceivers you want in the locations you want. The next thing to talk about is the tool chain. I mean, the tool chains can, really make a difference in your experience when developing with FPGAs and ease that transition. Those who developed with UltraScale Plus will be familiar with Vivado. That same Vivado tool is used with the Versal devices as well for the traditional top-level RTL flows. So if you've used Vivado before, you'll be familiar jumping into Versal and continuing to use Vivado as well. And you're going to do your synthesis and place and route, power estimation, and all those things in Vivado for the programmable logic. They've added, some features in the tool to support things like the SIPs and the NOC that Brett had mentioned before. But there are lots of example designs that show how to set those things up and use those. A tool that you may not be as familiar with is Vitis, and Vitis is used for some of the other processing elements that are in the part. So for the end-to-end application development, whether you're wanting to develop in C, C++ applications that are going to run on the ARM cores, or if you want to use high-level synthesis in some of those languages to implement an IP core that you're going to run in the programmable logic, or if you want to use the new AI engines and develop maybe some sort of digital signal processing algorithm to run on those AI engines, or an AI inference algorithm, you're going to be working in the Vitis tool for those kind of user application side workflows. And then the last thing I would note here is that you still have that extensive library of soft IP for the programmable logic as well, just as you are used to in some of the previous FPGA families. One thing I would note here, especially for those looking to make use of some of their previous designs, is that when you are porting, some of those soft IP cores that were available in previous devices may not be compatible with the Versal device anymore. So it's really important to go and check those things as you are porting those designs. One area that we've noticed is the XDMA IP core that was available on previous devices is no longer supported by Versal, but they do have other DMA options, including their QDMA, and the CPM hard IP block actually has hardened some of the QDMA capabilities as well, saving space and power in the programmable logic. So there are some benefits, but just be aware when you are trying to port a previous design. The next thing I would touch on is just board design considerations when you are putting some of these parts down on a board. These are some of the devices in the family, especially when you get up into the premium devices, can be very large. They can also consume a lot of power. And as you know, the FPGA device power is very dependent on the load that goes in them. So it's important to size the power supply circuitry accordingly. If you're looking at a 3U VPX card, for example, you're also going to have limits of what the slot can provide, and probably even more importantly, how much you can actually cool on that module in that slot. So these are all factors when you're trying to design that power supply circuitry, and making sure that you do have enough power there to support the capabilities of the device. The next thing is, these devices have added a lot of I/O as well. That's led to tight ball pitches that are used on these devices. So you want to be aware of this as you're designing. A lot of the packages are at 0.92 millimeters, even, and some of them are even smaller than that. So especially in this industry, if you're doing class 3 PCB design, you want to be aware of, transceiver blocks that you're selecting for your high-speed I/O and where those are routing, and make sure that you have enough room to get all of those signals out from under the part, and still, meet some of those more stringent, trace widths and via structures of class 3. And then the last thing that we found is just, kind of follows that theme of selecting the right, transceiver quads and hard IP flexibility, the way you orient the part and which transceivers you're selecting to go to the backplane versus elsewhere on the board. That can have a large effect on the feasibility of actually, routing some of the larger parts on the board. So these are all things to really think about upfront on your design. And in this industry where size, weight, and power is a big concern, being able to get some of these larger, more capable devices in the smaller form factors can be very important. And here on the right, you can just see a couple of boards that we've done at New Wave, one on an XMC form factor, one on a 3VPX form factor. I think the top part there is a VM 1802 from the Prime series. That's 45 by 45 millimeters. The bottom board is from the Premium series, a VP 1702. That's 55 by 55 millimeters. So you can just see how much of that board real estate is taken up by the part itself. The last section I want to touch on are the AI engines, and these are a completely new processing element that's available in the Versal series. So you won't be familiar with these from UltraScale Plus. And they were, specifically designed, as Manuel mentioned earlier, as you're trying to increase performance and reduce power. The idea was how we have all of these digital signal processing and machine learning, AI inferencing workloads that use a lot of vector type of math operations. How can you develop some silicon that is optimized to deal with those things and reduce power? So the AI engines came along for that reason, for those types of applications. And the idea is that for certain workloads, they're going to be able to provide increased computing in a smaller area, and also reduce power for doing similar types of DSP, AI, machine learning algorithms than you would be able to do using the DSP resources in the programmable logic core. So if this is something of interest to you, there's quite a few examples out there from AMD showing, especially on the digital signal processing side, how you can utilize the AI engines for those workflows. So I would recommend, if you are moving into the Versal series, to play around with those tools at the beginning and look at your algorithms and see if you are going to get any of the power benefits and see if it's worth making that transition from the DSP resources in the PL over to the AI engines. For a fresh design, that might make sense, or if you're really trying to reduce swap, that might make sense as well. If you already have a big algorithm that you already have working in a previous design, and you just want to port that over to the Versal series, that's always an option too. The one thing I would just make sure to be aware of is that you in the Versal series, especially in like the Prime AI Core series as well, you're going to have fewer DSP resources in the PL than you would have in similar size designs in the UltraScale Plus family. If you are running algorithms where you really need a large number of DSP resources in the PL, I would recommend looking at the Premium line, where you have some larger DSP resources there. So in closing, as you're as you're looking to do your next design, whether that's a next generation design or you're upgrading an existing platform with more capability, the AMD Versal ASoCs definitely do provide a leap in capability over some of the previous generations of FPGAs. But if you do make that transition, you have to really be looking to utilize some of those extra heterogeneous processing elements that are available and all that hard IP core that is available as well. If you've done FPGA design before and are familiar with some of the traditional FPGAs, I think you're going to make that transition pretty smoothly as long as you're aware of a few things and you do take the time to go, look at some of the example designs, maybe do some training and get up to speed on some of the new features like the knock and the SIPs as well. But there's lots of tools, methodologies, and examples that exist out there from AMD to really make that transition as seamless as possible. And hopefully we've provided a few things that we've learned along the way at NewWave today to help ease that transition as well. So if you're doing your next design, I would definitely seriously consider looking at the Versal series and how that new adaptive SoC architecture could help in your design. And if you have any questions, definitely feel free to reach out to NewWave, and we would be happy to discuss that transition to Versal with you. And with that, I'm going to hand it back to John, and we can have some time for Q&A.
Thank you, guys. Thank you, Ryan. Excellent presentation by all three. Let's get started on a Q&A. I got a question here, not assigned, so whoever wants this one, just grab it. For a sensor fusion application, what is the biggest risk we face implementing Versal when our familiarity is with ultrascale? Going once, going twice. Manuel's on mute. I can't hear him. Must be the shark. He's underwater, it looks like. It could be why.
Okay, can you hear me now? That was
yes,
strange.
Absolutely. Yes.
Okay. My speaker was not muted, but I just hit the button a couple times and it unmuted. Apologies on that. Okay, let me start, and then I'll probably pass it off to Ryan or Brett to follow up as well. But I think, Ryan did make some good comments in that vein. And so it does depend where you're coming from in the UltraScale Plus portfolio, because it is a very large portfolio. And then when you carry forward to Versal. So for example, if you're using high performance Vertex devices, Vertex UltraScale Plus for something like radar electronic warfare, there you've got an FPGA design. Now you're going to move it into an adaptive SoC. And ideally, you're probably taking other processors off the board, like maybe there's a CPU in that design as well, and you're integrating it all into a single Versal Premium series device, for example. And so in that case, yeah, there's going to be a new set of tools with regards to Vitis, using the processor system and programming it. And then you're going to, of course, incorporate that code into a single device, as opposed to before where you had multiple devices, probably an FPGA and a CPU, and quite likely multiple of those, of course, in a design. If you're coming from someplace like Zinc UltraScale Plus, where you already have familiarity with an integrated design, in that case, of course, it uses quad A53s with Versal Premium Series. The first generation, we have dual ARM A72s. That's going to be pretty similar. You're already going to be used to having to use Vitis, although you might have used an earlier tool set from, if you were using the tools from 5-10 years ago. But the concept is still the same. You're going to be fairly familiar. So that transition is actually a lot easier to do. You've already got a design that's integrated, and now you're just going to increase the performance or add new functionality and add new features. So it's certainly more straightforward than if you're moving from Vertex with an external processor into a Versal adaptive SoC. Ryan or Brett, do you want to maybe comment from the board level perspective?
Yeah, I would just add too. I agree. If you're coming from a Zinc MPSoC device that already had those cores, I think the transition will be a little more seamless. If you haven't done that before, there's a learning curve there, but I think it's definitely manageable for anyone. I would also say, yeah, the biggest thing to be aware of are just, you know, the biggest gotcha I think we had right away was just the fact that that the CPM, which is really nice and really useful, does not support you know, anything besides PCI Express. So that's something to be aware of, especially in this, you know, industry where a 3U VPX card, you might, on that expansion plane, you might want to support different things. So on the board design, for example, we were able to accommodate that with doing some muxing on the board to make that available. But that was a big not something hard to overcome, but just something that we hadn't encountered in previous FPGA designs.
Yeah, I think that's an excellent point, Ryan. Maybe I'll tag on to that a little bit. So that's feedback that we've received and heard at AMD, and of course Xilinx before AMD acquired us. And so if you look at something like the Versal Premium Series Gen 2, which I didn't have time to talk about much, but since we have a little extra time here, aerospace and defense is absolutely one of the target markets for Versal Premium Series Gen 2. In particular, things like radar, electronic warfare, other high performance applications where you need to do a lot of signal processing. And one of the things, if you go look in detail at that series, it's all on the web, you will find that there is a rectangular package. It's actually the first Versal rectangular package that we will have done. And the reason that we did that design is specifically actually for 3U VPX design. Right. And so having a large square package in the middle of a 3U board, of course, can be problematic. So moving to a rectangular package is much friendlier from a size perspective. However, we also made sure we designed the package so that you basically at the top have access to all the memory controllers so that you can place all the memory at the top of the 3U VPX board. And then the SerDes are all packaged out at the bottom. And so basically you have all the SerDes, which can then run straight out to the backplane. Right. And so to that point that you just made, Ryan, we have taken that feedback and we do have devices like coming out in the Versal Premium Series Gen 2, which will start to be available early next year, and where we've accommodated that feedback and actually designed specifically for things like a 3U VPX design.
Yeah, and I would agree with that. You know, some of the feedback that has been provided, I think with the Gen 2, a lot of those things were addressed, and we're excited to look at those parts as well. So,
got a question here from the audience. Next one. If I have a traditional RTL design that I want to integrate with AI engines and the PLIO, any comments on the best any comments on the best tool flow path to use? Who would like that?
Yeah, let me start with that one as well. Let me make sure I understood the question correctly, John. So it sounded to me like someone has an existing design that may already be running in RTL that they may want to move into AI engines. Did I understand that part correctly, John?
Right. I'll read it again. If I have a traditional RTL design that I want to integrate with AI engines and the PLIO, any comments on the best tool flow path to use?
Yeah, so you know, I'll hand off to Ryan in a minute, and he did have a slide on that. Maybe it makes sense to bring that slide back up. But yes, when you look at AI engines, I mean, fundamentally, it is a processor architecture. You do have an instruction set architecture, so it's not programmed with RTL. You do use a flow that's part of the Vitis flow. And so it's C-like. It's not exactly C or C++, but it's C++-like, you can think of it as. And what I would say is an RTL design does not really translate, quite honestly, to the tool flow you'll have with AI engines. The best advice I have for folks, and when we have many customers that have been in that similar scenario, is to go back to first principles and typically look at things like your reference C model. Because in many cases, you will have a reference C model, or maybe you have a MATLAB model. That is the best starting point. And then taking that reference C model, for example, and putting that into the Vitis AI engine tool flow and work around C++ and parallelizing the design at that point is going to be a lot easier than trying to start from RTL. So again, start with the reference model, whether it's C++, even M code. You know, it's fairly straightforward. It's not easy necessarily. Ports always involve a lot of complexity, but being able to take that into the AI engine tool flow is definitely the approach that should be recommended. You do not want to start with RTL. It just won't port, quite frankly. Ryan, Brett, did you want to add anything to that?
Yeah, I would agree. I think it's really helpful to start with your model, of your algorithm to begin with, versus just. I don't think there's a good tool out there that's just going to take your existing RTL design and magically make it work in the AI engines. So you kind of have to start from that spot. I think there's some good resources on AMD too, from talking about especially like DSP, how to get your DSP algorithm up and running on the AI engines. I think that's useful, and there's some examples out there that do that as well. Even that have some that are in the sensor processing domain as well. But if you really have something that already works and you want to port it over, I would also consider is it worth it to take the time and energy to get them to run there? And maybe it is for swap purposes or to reduce power. Maybe it's better to get into a device that has the DSP resources available too. And the family includes us, both ways. You can go at it both ways.
So the questioner behind that one said, "Hey, thank you for your answer." He goes, but he should have clarified. He goes, the question is integration between AI engines and PL, not porting. He wasn't
Yes.
clear.
And yes, and I saw that as well, John. And that, thank you for clarifying that, Alex. That's perfect. Yeah. So what I would say is that is definitely something that needs to be taken into account in the design. As you map out the entire design, you do want to determine what makes the most sense to go into the engines, what makes the most sense to go into the programmable logic and the DSP58s, and what, of course, should go into the processor system as well. At that point, yes, you do have to integrate, and you will have all these things interacting with each other. Even the PS will be doing control and the operation of the entire system level. What I would say is we do have a lot of reference designs on the AMD GitHub, so you can find, and those are all available with open source code, by the way. So that's a great starting point to go look at those designs and understand, okay, what was the interaction between the AI engines and the programmable logic? And a couple things to keep in mind as well is we do have a couple of different versions of AI engines, right? So we have the original AI engine, which came out with AI Core in the first instance of the Versal devices that came out to market. Excuse me. But now we also have something called AIEML. And so that's a version of the AI engine that's a little more oriented to around machine logic, ML and machine learning and AI, but it still does have support for DSP functionality. And the addition with the AI and AIEML, one of the big additions to the architecture was that we added something called memory tiles. The reason we added the memory tiles was a recognition that with the original AI engine, you actually ended up having to use some amount of the programmable logic as a memory buffer, right? And look, we have a very high bandwidth interface between the AI engines and the programmable logic. So we have a shim that helps manage that. However, it's optimal, we found, if we could put in the memory tiles, and then you don't have to cross the shim and go out to the programmable logic and then come back in. And so that's something that you need to take into account with the AIEML architecture. Should actually improve performance, should lower latency. So there's a lot of advantage to that. But then again, you will also then have a different interaction with the programmable logic. And quite frankly, you shouldn't have to go to the programmable logic nearly as much as you would with the original AI engine. So these are things you do have to take into account. And again, we do have a number of reference designs. We have reference designs for beamforming, both for commercial 5G wireless systems as well as for radar systems. We have a space-time adaptive processing algorithm. So there's a lot of things in there. I think we also have a music algorithm for direction finding. So we have multiple designs in there, which are a great starting point for going in and understanding how these things have to interact, and then working within the Vivado and the Vitis tool flow to then have all these things interact together and debug at a system level, which you can do for those tools. So you will again use Vivado and Vitis. But I think the reference design is a great starting point to make sure that you've designed your system well.
Okay, next question is from the audience. How will my power requirements change when I transition from an ultra-scale FPGA to a Versal device? Ryan or Manuel or Brad, who would like that one?
I can jump in on this one. In general, to kind of start with a story that is kind of around static power, NewWave has pretty capable designs for example, a fiber channel network interface card. And that will be, an XMC board power of, around 10 watts. Whereas we've done some recent estimates with VP1702s on some of our 3U VPX cards at their expected junction temperatures. And it's been a static power for one chip of the design of 26 watts. So it's like, on the one hand, it seems like you're going to have extremely high static power. And I think that's an accurate statement. However, when you look at the swap of what you're doing, so you have a lot of hard silicon, you have, MR max and DC max and CPM for PCIe capability and hard memory interface controllers and the NOC. When you look at the total swap, if you have a sufficiently large design, your power requirements in general are going to be higher for the ASIC because it is a very large, chip. But from a capability perspective, you're going to have a better swap performance. So to kind of summarize that, I would expect your power to go up, but I would expect your capability to go up more. So your swap is going to improve.
Yeah, no, I think that's good, Brett. I guess a couple of comments to add to that. So it is important, to your point, to look at both static and dynamic power. Excuse me. It's just a well-known fact that as you move to smaller nodes, leakage increases, right? So that, of course, means your static power will go up. And that's just one of the realities when I talked about in my charts about things that, we needed to take into account moving forward when we were thinking about the Versal architecture. That was absolutely a big thing we had to take into account because we knew that static power was going to increase. So we had to bring more to the table from a dynamic perspective to compensate for that, to your point, Brett. The other point I will add is that we do have within Versal an option for every single one of our devices. This is a standard SKU. It's nothing special to do a low static screen. What that means is across the plethora of devices that we have, of course, some of, those go into different bins based on where they turn out in terms of performance versus power consumption. And we have ones which will end up a little lower on the curve in terms of static power consumption. And those devices then we will put into a bin where we specifically screened for low static power. And so that is one of the options when you choose your SKU within Versal. Every device has a low static screen option. And so taking those devices does mean that your static power consumption would be lower than the standard devices which don't have that screen.
Okay.
Yeah.
I was
just going to say, the only thing I would add too is I think, we've noticed this and we're excited on some of the Gen 2 devices. I think you've added some more capabilities of turning different things in the part off if they're not being used, right? So you might not take as big of a static power hit as you did on some of the Gen 1 devices.
Yeah, no, that's an excellent point, Ryan. Absolutely, we've done that. It does, of course, the more control that you add, of course, it means the more power rails you need. And so it does make your power design more complex. And so that's one of the considerations you have to take into account. But that's just the reality of being able to trade off all of that capability. And of course, you can consolidate power rails if you don't need that full amount of trading off power versus performance. But in this case, I would expect a lot of customers would want to do that. And of course, I think some of the value of the boards that you've developed, Ryan and Brett, and some of the system level stuff that you've done is that you start looking at the power and looking at the whole power system and making sure all that is accommodated for in your board design.
Mm-hmm.
Okay. Next, I think I have time for one more question here. From the audience, do you have to change the code to take advantage of the NOC? Who would like that one?
I can start with that one as well. So the network on chip, what we call the programmable NOC, really did not exist prior to Versal. And so really the way to think of it is kind of a super highway that moves data very efficiently across the device. And especially when you have a large device, that's even more powerful because, moving data, having to route it through all the programmable logic is less efficient than just being able to place it on the network on chip and boom, have it move up to wherever it needs to be next in the design. So because it's new, there is a tool that does allow you to basically develop the data movement, if you will. And it's called the NOC compiler. The NOC compiler is basically part of the the tool set that you bring up at the start of the design, like Ryan and Brett covered. And so that is new. It does mean when you're looking at designing with Versal, you do need to think very early on about your data flow and how you're going to move the data, because you are going to then go into the NOC compiler. And it's very easy to use. It's very intuitive. And you can basically then start putting in, what's pretty similar to pretty basic coding, and start graphically seeing, okay, how is this going to map? Am I going to end up with bottlenecks here? Okay, then how do I move the design to make sure that I'm not going to get bottlenecked there? And so you have a lot of capability within that NOC compiler, but it is new. So that is one of the things that moving from Vertex or even Zinc UltraScale Plus to Versal has to be taken into account. But again, at the end of the day, it does mean that you have a much higher level of confidence as you're going through your design, that the design will place and route, that the data will not get bottlenecked, that your system will be very functional and very effective. Ryan, Brett, you want to add to that?
Yeah, I would just say in general, I mean, the NOC is something that's new. You have to figure out how to use it. But in general, once you learn how to use it, we've been very happy to have it available, especially when trying to get, cross SLR regions, get to one side of the chip to the other. It makes it a lot easier on the back end with not having to fight place and route. So.
Oh, we lost you, John. I think you're still on mute.
You lost me because I didn't take myself off mute. Moderator error, moderator 101, right? So I got time for one more question, guys. We got a few minutes here. So of all the risks presented today, to migrate into the Versal family, what's the most important element to consider? Who wants to start? Brett, Ryan? Or start with the top of the alphabet, AMD.
I mean, I can go from my perspective. I think, obviously coming up to speed with some of the new pieces is important, but I think once you do, it's been nice to design with the part. And I do think it's really important that you need to make use of all of these new features that they've added. If you're just going to take your same design and implement it all in the programmable logic, you're not going to take advantage of any of the new capabilities. So I think it's really important to understand and think about and architect your design in such a way that you are making use of all the hard IP, you are making use of the AI engines if you have them, you are making use of the processor subsystem in those cases, and that's when you really get the true capabilities of the device.
Yeah, no, that's a great response, Ryan. The hard IP is one of the biggest things that differentiates Versal. And honestly, if you find in a design you don't need a lot of the Versal hard IP, maybe you just stick with an UltraScale Plus device, right? And so those are the things that you have to put in your head and consider. But definitely, when you can take advantage of a significant amount of the Versal hard IP, you are going to end up way further ahead. You are going to find that the design is a lot easier to actually develop. And so your development costs should go down because you're not having to develop things around Ethernet or PCIe. It's all just done. And so a lot of that is you'll get to market faster, I think, basically with Versal, once you've got used to having things like that hard IP and a network on chip that we talked about earlier. What we've actually seen from our experience is for folks, especially moving from Vertex, there's that initial ramp moving from Vertex to Versal, and there is a learning curve associated with that. So there is a bit of a learning curve, and that takes a bit of time. What we found was after that first design was done, successive implementations, like maybe they're adding features later, or maybe they're moving from 16 antennas to 32 antennas. At that point, adding and modifying the design is very easy, far easier than what they had to do in previous generations of FPGAs and adaptive SoCs. So with Versal, again, there's a little bit of a learning curve to get in. Once you're in with the architecture, we actually find it's actually far more productive once you've made that initial transition and you're able to modify and grow or shrink the design, because we have a very scalable portfolio of small to large devices very, very quickly, far more quickly than you could have done previously.
Thank you, gentlemen. That brings us right to our time limit for today. Sorry we cannot get to all of your questions. Someone may get back to you after the event with more information. I want to thank Ryan, Brett, and Manuel for speaking today, and New Wave Design for sponsoring this webcast. This and all Open Systems Media webcasts are copyrighted, may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as the URL shown on your screen, and will be available for at least 1 year. I look forward to seeing you on future Open Systems Media webcasts. Goodbye and have a great week. Thanks everybody.
everyone.
Great job, guys.